So far when we've been talking about finding the integral and using that to find the area under a curve between 2 points A and B on the x-axis, what we've been talking about is going from some top curve all the way down to the x-axis and finding that entire area. Well, what happens if we change our minds a little bit and we say, well, I don't want to go all the way to the x-axis, I want to go between my function and some other function. So I want to shade this region S here that's below f of x but above g of x. Well, what we can do, or what we would think of doing, is we could take the area under this first function, this big function f of x, and we can take the area of this other function g of x, and from there we would take the area under f of x and subtract off the area under g of x. So if f of x is greater than or equal to g of x for all the values of x between 2 points, then the area under the curve, or between the two curves, is going to be the integral from a to b of f of x minus g of x dx. In other words, it's the integral from a to b of f of x dx minus the integral from a to b of g of x dx, which translates to the area under f minus the area under g. So as an example, say we wanted to find the area of the region bounded above by y equals x squared plus 1 and bounded below by y equals x between 0 and 1. So we are starting here, ending here. Here is y equals x. Here is y equals x squared plus 1. And we are interested in finding this area between them and between 0 and 1. So how do we find that area? Well, what we'll do is we'll take the integral from 0 to 1 of x squared plus 1, which is our higher function, minus x, which is our lower function, dx, which is just the integral from 0 to 1 of x squared minus x plus 1 dx, which means we have x to the third over 3 minus x squared over 2 plus x being evaluated from 0 to 1. So what will that look like? That'll look like 1 cubed over 3 minus 1 squared over 2 plus 1 minus 0 cubed over 3 minus 0 squared over 2 plus 0. Or in other words, it'll end up being 1/3 minus 1/2 plus 1 minus 0, which will end up giving us a total of 5 over 6. So sometimes we are given these bounds, these a's and b's, and sometimes we want to go ahead and figure out where they intersect. So say we wanted to look at the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. So first we need to find where these functions intersect. Okay, so how do we do that? Well, we can draw kind of the general graph. This in general is what y equals x squared looks like. this is about what y equals 2x minus x squared looks like. But that doesn't really tell us a whole lot. And you might not know this offhand if you were trying to kind of spitball or quickly graph what these would be. So the question is, how do we know where they intersect? Well, we're really just setting them equal to each other. So we're saying that x squared equals 2x minus x squared. So we want to know what the values are for x that makes this true. Well, if we get everything to one side, we would get 2x squared minus 2x equals 0, which is the same as 2x times x minus 1 equals 0. And so that means that 2x equals 0, or just x equals 0, is one of our places of intersection, and x minus 1 equals 0, or just x equals 1, will be another place where we have an intersection. And so we want to figure out where exactly it is that we're looking at, and which one's our top function and which one's our bottom function. In order to figure out what our top function is, we'll figure out what the values are between these places where they end up intersecting are. So this is our area that we're trying to find. It's enclosed between the two values. So say pick x equals 0.5. The reason we're picking 0.5 is it's between 0 and 1. Well, then y equals x squared would be equal to 0.5 squared, which 0.5 squared will just be 0.25. And we'll look at y equals 2x minus x squared, which will be 2 times 0.5 minus 0.5 squared. So 2 times 0.5 minus 0.5 squared will be 0.75. So this is our higher function, this is our upper, and this will be our lower. So with that in mind, knowing where our upper and lower are, the area between these two will be the integral from 0 to 1 of 2x minus x squared minus x squared dx, which will be the integral from 0 to 1 of 2x minus 2x squared dx. Taking the antiderivative here, this will be 2x squared over 2 minus 2x cubed over 3, evaluated from 0 to 1, which again will just be x squared minus 2/3 x cubed, evaluated from 0 to 1. That means we'll have 1 squared minus 2/3 times 1 cubed minus 0 squared minus 2/3 times 0 cubed, which will give us 1 minus 1/3 minus 0. Sorry, 2/3 minus 0. Jump the gun a little bit, which will give us 1/3 as our area between those two curves. All right, now sometimes the area we're going to look at won't just have one top function and one bottom function. Sometimes we'll have things where the function in the numerator and the function in the denominator switch as far as which ones, or sorry, not numerator and denominator, the function that's above and the function that's below will switch as far as what should be the upper and lower on the integral. So we'll have, in this picture here, we've got g of x is this function that starts below, then is above, then is below again. And f of x starts above, ends up below, and is above again. So we always want larger minus smaller, or in other words, the top minus the bottom. And so for this first region, we would integrate with f minus g. The second region, we would integrate with g minus f. And the last region, we would go back to integrating with f minus g. And remember, we're allowed to break apart our interval and our integral in order to find the different pieces. So we have here 3 separate integrals. So say we wanted to find the area of the region bounded by the curves sine x and cosine of x on the interval of 0 to pi over 2. When we look at 0 to pi over 2, recall that cosine of 0 is 1 and sine of 0 is 0. But when we get to pi over 2, they switch roles. So we start sine at 0, and it becomes 1 at pi over 2. So this is our sine of x. And we start at 1, and then we go to 0 at pi over 2, and this is y equals cosine of x. So we are interested in finding two different regions. We want to find this region here, where cosine is larger and sine is smaller, and we want to find this region here, where sine is larger and cosine is smaller. So the question will become, where do these two meet? Where are they equal? And this one's going to have to rely on you knowing a little bit of the unit circle. But this point here where they intersect is pi over 4. So that means if we want to find the area, this will be the integral from 0 to pi over 4 of cosine of x minus sine of x dx plus the integral from pi over 4 to pi over 2 of sine of x minus cosine of x dx. So this here is how we look and find S1, and this here is how we're going to go ahead and find S2, those two different areas. So if we take the antiderivative then of this first one, we will end up with sine of x plus cosine of x, and we'll evaluate this from 0 to pi over 4 plus the antiderivative of this, which will be negative cosine of x minus sine of x, evaluated from pi over 4 to pi over 2. So there will be a lot of bookkeeping here, so be very careful about how you do things. I'm going to have our picture kind of put off to the side here. This then is the sine of pi over 4 plus the cosine of pi over 4 minus the sine of 0 plus the cosine of 0. And this is for this first region. Plus negative cosine pi over 2 minus sine of pi over 2 minus negative cosine of pi over 4 minus sine of pi over 4. Alright, we got 4 pieces here. It's a lot to break down. This will end up becoming sine of pi over 4 and cosine pi over 4 are both the square root of 2 over 2. So this will be root 2 over 2 plus root 2 over 2. Minus the sine of 0 is 0 plus the cosine of 0 is 1. So this is this one, this is this one, plus the cosine of pi over 2 is 0, so negative 0, minus sine of pi over 2 is 1, so minus 1, minus negative cosine of pi over 4, so negative root 2 over 2, minus sine of pi over 4, so minus root 2 over 2 again. So this root 2 over 2 plus root 2 over 2 will be the square root of 2. If we have 0 plus 1 and we're subtracting that, that'll be minus 1. If we have 0 minus 1 and we're adding that, that'll be minus 1. And if we have negative root 2 over 2 minus root 2 over 2, that'll be root 2. And then negative root 2, and then subtracting that will give us a minus a negative square root of 2, which when we're subtracting a negative, it ends up being a plus. And that means we'll have 2 square root of 2 minus 2 as the final value of this integral. There are a lot of steps here, so do make sure you kind of pay attention. Negative signs are killers on these, so be very careful as you look at these. All right. We want to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So here, this is a little bit tricky because we're not used to having a y squared. So how are we going to face this problem? Well, what we'll do is we'll actually look at things in terms of y and make y our variable. So make y the variable instead. So if we know that y equals x minus 1, this is the same as saying that x equals y plus 1. And if we know that y squared equals 2x plus 6, this will be the same as us saying that x equals y squared minus 6 divided by 2. So we want to rewrite those so that we have x in terms of y. And now we'll have to figure out where we are intersecting. So that is going to be our first step for this problem. Y the variable instead. Maybe I'll clarify by solving for x in terms of y. So that's how we start things off. Next, we'll go ahead and find intersection. So that means we'll be setting y plus 1 equal to y squared minus 6 over 2. If these are equal, then 2y plus 2 will equal y squared minus 6, and that means that y squared minus 2y minus 8 will have to be equal to 0. From here we can go ahead and factor. So we'll get y minus 4 times y plus 2 equals 0. And if this is the case, then y equals negative 2 and y equals positive 4. And so these will be our limits of integration. From here, we want to figure out which is the higher and which is the lower. So we'll pick some point in the middle to know which is the one we should be having as our first function versus our second function. Now here it's kind of hard to think about having a left versus, or a top versus a bottom, but for us it'll be a right versus a left. So say this is kind of a quick sketch of what's going on. We've got some line here as y equals x minus 1, and we are trying to then look at the parabola. This is not perfect. Y squared equals 2x plus 6. And how we'll be integrating is we will be taking and going this way. So it'll be the right minus the left instead of the top versus the bottom we've been thinking about. So say we wanted to figure out which was the top and bottom, or first and second. So what we can do, we can again plug in a point in the middle between where their intersections are. So here if we pick y equals 0, then x equals y plus 1 equals 0 plus 1, or just 1, and x equals y squared minus 6 over 2 equals 0 squared minus 6 over 2, which is negative 6 over 2, which is negative 3. So this is bigger, so put it first. Alright, so say we wanted to go ahead and then find the area. Area here will be equal to the integral from negative 2 to 4 of y plus 1 minus y squared minus 6 over 2 dy. So this first one was our right function. This was the bigger one. And this was our left function, which is our smaller one. Now, because I'm kind of out of space, I will give you the answer for this one. The answer here ends up being 18. So from here, we're doing the same thing we've been doing for other problems. We are taking the antiderivative. We are plugging in our bounds and doing what we need to do as far as that goes. If you have questions on how we get from here to here, definitely post about them in the discussion board. It'll be kind of a nice little bit of extra practice and an opportunity for you guys to kind of work through together how you get from something like this to something like this.